Hello, everyone. Welcome to my talk on breaking black box AI. So, good morning to all over the world. I am Evelina Gabasova, and I work as a research data scientist in the Alan Turing Institute, which is the British National Institute for Data Science and Artificial Intelligence. And I'm part of the research engineering group. Uh, just a note, if you are in the UK, the Turing is now organizing a COVID-19 task force of data scientists, research engineers, and AI researchers. And it's open for anyone to sign up by today, I think. So look it up if you are interested in that. My background is mostly academic, but my well, I've worked in bioinformatics, I worked in various sorts of like mathematical modeling areas, but the most academically successful thing I ever did was to produce a Star Wars social network that I published. So if you are bored at home, just look it up. Right now, my main project is in air traffic control, where we are investigating various methods on how to do something like reinforcement learning for air traffic control. And we developed a simulation environment where you can try your own agents to direct traffic. Well, with the current situation in the air right now, that's no longer a problem, that there would be too much traffic. But we can prepare for when things return to normal. I want to talk about how we do machine learning right now in 2020. It's a very, very active area. A lot of people love to do machine learning, they love to do AI. And the great thing is that right now, if you want to do AI, there are so many libraries and so many toolkits where all the fancy stuff that 10 years ago took you like a month of developer time to actually implement, it amounts basically just to a one-liner that you call your fancy model, you call anything you want, and it just does what you want it to do. Is that really true? We'll look at that today at my talk. And the great thing is you don't even have to spin up things like TensorFlow yourself, etc. You can just call some API. Google has its prediction API, Amazon has machine learning, Microsoft has cognitive services on Azure. And you can use any of those. You don't really have to understand what's happening behind them. You just call them and they give you things like descriptions of images, etc. So that sounds perfect, right? Because really 10 years ago, it looked more like the thing I have here on the right, where you had to go into a textbook, look up all the equations, implement them, test them, etc. And after a few months, you had something that could be used potentially, or things were still a research problem. But right now, we are like the picture on the left, where we basically don't need any mathematics anymore. You can just literally call a one-liner, you can call an API, you can call a function that's already implemented somewhere, and it does all the AI magic. That sounds too good to be true, right? Well, I like to use the metaphor of a compiler compared to machine learning systems, where if you are a programmer and you use a compiler, which basically everyone does, you don't really have to understand what's happening underneath. You don't have to understand all the lexing, tokenizing, parsing, constructing abstract syntax trees, etc. You don't need to know any of this if you just want to compile your program in your favorite language. And we are trying to get there with machine learning so that you don't have to understand all the linear algebra, you don't have to understand all the derivations, etc. But the problem is that we are not quite there yet. Basically, software development and machine learning are very, very similar. You implement some algorithms, they do their thing, they get their inputs, they process them in some way. they spit out some outputs. And you can have things like implementation bugs in both. But the problem with machine learning is that you can still have bugs that are caused by the fact that it's a black box thing. And if you don't really understand how it works underneath, it can fail silently and hurt you. So I'll be looking at a couple of examples of this and hopefully give you a warning. And by the end of this talk, you should be paranoid whenever you are using any kind of black box machine learning or AI system. So let's look at black box machine learning or black box AI. What do I mean by that? Well, the rules for the rest of this talk is that I will be using algorithms out of the box with minimal setup from various popular libraries or machine learning APIs. I will try to keep mathematics at a minimum. And just let's observe where things go wrong and why. So let's start with the hello world of machine learning, which is linear regression. If you consider linear regression to be machine learning or not, that depends on you. Probably depends on if you want to sell the system or not. But linear regression is basically the simplest model that anyone doing machine learning starts with. And let's look at some practical demos, actually. And I don't want to be doing any kind of opaque, just present you with results stuff. I want to do everything as transparent as possible. So I will just use Jupyter notebooks. So here are my demos. So let's look at linear regression. And I'll be using various different languages throughout this talk. The first one is in R, because linear regression is basically one of the basic constructs in R, because R is more sort of a DSG for doing data science rather than a proper programming language. And I'll be just showing everything live as a slideshow directly from my Jupyter notebook. So let's look at a linear regression demo. Let's just load some libraries. Okay, everything is loaded. I will give you a link to these notebooks later on so that you can play with everything yourself as well. So first thing we will do is we will simulate some data. This part of the talk is probably the most mathematical one. So what I did here is basically I just simulated a random noise, the R norm. Let's shift things a bit. So the R norm function in R basically just simulates from a normal distribution with zero mean and unit variance. So I simulated 100 points where the x-axis, or the x value and the y value are random noise that's normally distributed. So there are basically no patterns here. It's just a random blob. Okay. So how do we do a linear regression? In R, you use the LM function, which stands for linear model. And here I am doing a prediction of y, how it depends on x, which basically just computes this equation. I have my x values and my y values, and I'm trying to infer a and b using my simulated data. And then just compute a summary of the model. Okay, so let's evaluate this. I'm trying to delete the annotation, but the keyboard shortcut is somehow interfering with Zoom. So sorry about that. So the things to look at right now, I just produced a summary of the model that I created. So two values to look at whenever you are assessing how well a linear regression fits is the p-value here, which tells you what's the probability that we are getting this result by chance. And right now it's 40%. So that's a fairly large probability that we are just getting this by chance and it doesn't mean anything. And the other thing to look at is the r-squared value here, which tells you how much variance in y can we predict using x. And we can predict basically zero variance. So together, the r-squared and the p-value tell us that this model is completely rubbish. And that's expected because I'm just trying to predict random noise from random noise. But what if we add one data point, one single data point in addition to the original ones? So these are my original data here. And I added one data point that's way outside of the range of the data. It's the value 100, 100, whereas all the other values are around 0. And I fit another model on that. So let's see what happens. Exactly the same model, exactly the same data, apart from one single data point. Well, suddenly my p-value is basically 0. That means there is 0 probability I'm getting this model by chance. And my r-squared is 98%, which means my data, I can, using this model, using basically just random noise plus one extra outlier, I can predict 100% of the variability in the data using this model. So based on just these numbers, the model looks perfect. And if I didn't know that there is just one single outlier, if I didn't look at the data, I would have no idea, because now this model looks perfect. It can basically do its job. It can predict all the variance in y using x. That's a problem, because if we have something more real world, for example, here I have a random data set that you can yourself, which looks at bike usage in a Washington, D.C. bike sharing scheme based on the weather and if it's a holiday, if it's what day of the week it is, what's the weather, what's the temperature, etc. This is just an example of the data set. And for each day, based on temperature, humidity, wind speed, holiday status, it looks at how many people borrowed a bike that day. If I run a simple linear regression model on that, this is again a summary that R produces. If I look at my p-value, it's basically 0, which means that using my predictors, which in this case is the weather situation, temperature, day of the week, season, and if it's the first year or second year that the scheme was running, my p-value is basically 0, which means my model is predicting something. I'm not getting these results by chance. And my r-squared is 80%, which means I can predict 80% of the variability of the data with my inputs. That basically tells me this model is fairly okay. What if I add another data point that's just manual entry? Someone is trying to fix the data. Let's add another data point where it will be just the first row. And it's data from the US. So let's set the temperature to 100, because obviously it must be Fahrenheit. And 100 is a nice hot day. So let's augment the data like that. And let's run another linear regression based on the new data set. My p-value is still basically 0. And my r-squared dropped to 73%, but it's still quite a lot. And if I didn't look at the data, I wouldn't understand why this is happening. The reason my multiple R squared dropped is that the temperatures are not actually in Fahrenheit. They are normalized into 0, 1 interval. But without actually looking at the data, I have no idea. So that's the first conclusion. Always look at the data. Let's go back to my slides. So with linear regression, if you studied linear regression, you are probably saying, well, this is obvious. If you have outliers in your data, then obviously linear regression is not going to perform very well because you have all these assumptions that are violated. And if you look at Wikipedia article on linear regression, you will see this huge list of factors and assumptions that have to be sort of valid before you can use linear regression in any meaningful way. But they use things like weak exogeneity, homoscedasticity. You are expecting lack of perfect multicollinearity. And if you are not a statistician, what do these things even mean? And thing is, you can't really expect everyone to validate or to use such a simple model as linear regression on their data. And none of the libraries that actually do linear regression checks these for you. They assume that you know what you are doing. But a simple one outlier can completely mess up your results. And I believe this is partly a human-computer interaction problem, where people just write libraries assuming that when you are using them, you understand what you are doing, and you understand the underlying model, and you are aware of all the assumptions, and you are yourself checking if all the assumptions are not validated. But this is just not reasonable in the real world. So there needs to be much more work. And if you are doing any kind of machine learning library or using anything like that, be aware that people are not reading the small print. People are just using the algorithms without checking any assumptions. And that's when things go wrong, because you don't validate all the assumptions that are sometimes fairly elaborate, and things go wrong silently. So let's look at another example, another very basic method called the decision tree, which is one of the strong workhorses of machine learning right now. It underlines all these random forest models that are probably the most used machine learning models in practice. So let's go into my Jupyter notebook again. Oh, sorry. Let's look at decision trees. So first, another Hello World application in machine learning, which is the Titanic data set from Kaggle. Here I'm using Python, because why not? Let's switch the languages a bit. And I'll be using scikit-learn to fit a decision tree. And this is an overview of my data set, which is basically just a data set of people who were on the Titanic and if they survived or not. So for every patient, I have an indicator if they survived or not, 0 or 1. I have the class that they traveled in, this is the first class, second class, third class. If they were male or female, what was their age, if they traveled with siblings or family, how much they paid for their ticket, if they had a cabin where they embarked on Titanic. And that's basically all. So let's fit a decision tree. So the first thing we have to do is to actually change some of these input data, for example, male and female, into 0, 1, so that they become numeric. So this is exactly what I did here. So now I just ended up with a giant matrix, and this is the data form that I can work with when I'm working with a decision tree. And let's fit a simple decision tree to the data, and let's see how it looks. So this is a decision tree visualized. I don't really want to go into details of how a decision tree is constructed. That's not what this talk is about. I want to talk about how it classifies the data. So it's basically a decision diagram where in every node, you look at a value of some of your predictors. In this case, it's looking at the numerical sex value. And if it's smaller than 0.5, then you go left. And if it's larger, you go right. So in this case, if the numerical sex attribute is 0, it means it's a male. If it's 1, that means it's a female. So in this node, it basically asks you, okay, is the passenger male or female? If yes, then go left. If no, go right. If the passenger is a male, then it asks about age. If the age is smaller than 7, then go left. If it's larger, then go right. And basically, you continue like this throughout the tree until you get to a leaf node, which tells you what class they end up with. And this is survived, this is died. So basically, if you look at it, the only way to survive on Titanic based on this very simplistic model is, if you are a male, is to be younger than 7 and have less than 3 siblings traveling with you. It means small family and young age. If you are a female, then you have larger probability of surviving. These two nodes basically contain just surviving passengers. So if you are a female, then the first node asks you what class you were traveling in. So it's very, very easy to interpret. It's very, very easy to go through. And you can see exactly what's happening in the model, which is great, right? All this movement for interpretable machine learning models, it should be fairly easy with decision trees. Well, let's look at some more interesting example. So let's load up scikit-learn again. And let's just generate some random data. So this is my data set. And you might be looking at it and thinking, okay, what's happening here? Basically, my data right now are combinations of X and Y values. So this is X. This is Y. And if I will go back to where I'm generating the data, basically, if X plus Y, here it's X train, etc. If it's smaller than 100, then the resulting class is 0. If it's larger than 100, then the class is 1. So basically here, if my X plus Y value is smaller than 100, it falls within the green triangle here. And the class is 0, or just class A. And if it's larger than 100, then it falls into the orange triangle, and the class is 1 or B or whatever you want to call it. So let's train a decision tree on that. And this is how it looks. So I just want to reiterate that this is basically just a decision tree trained on a data set with 2 input variables, X and Y, or X1 and X2. And if you zoom into it, It's basically just asking, okay, is X smaller than this value? Is Y smaller than that value? Is Y smaller than this different value, etc. And it's a very, very simple problem, but still the decision tree that's produced is this gigantic thing that, at least based on my opinion, it's not interpretable at all. Because if you see such a huge decision tree, you are thinking, okay, this is a complicated problem. Although I just had two input variables and the class is based on their sum. If the sum is smaller than the threshold, then it's something one class, and if it's larger than the threshold, then it's the other class. And the problem is that decision trees expect just very tabular data set in a sort of table where you can slice it orthogonally, where each input value basically just slices the data set in an orthogonal way where it doesn't depend on any of the other variables. But once you have interdependencies between variables, then you end up with something that's not interpretable at all, even in very, very simple cases. So this is just a warning that decision trees, they are considered to be very interpretable, very transparent, but it very strongly depends on how your input data look like. Let's again look at some real world example. This is an example from my colleague, where she looked at one Kaggle data set where they were trying to predict how successful a project, a school project, will be in raising money in a crowdfunding platform. And I don't want to go through the actual notebook. If you are interested, I will give you a link to all the notebooks at the end of the talk. But it's a fairly simple data set with 26 columns. Not all of them are used for prediction. So all over you have something like 20 input variables. And my colleague did a very good job at analyzing the data and doing the proper sort of thing you should do whenever you are doing a machine learning task, splitting the data, looking at precision, recall, tuning the parameters, etc. And she was very proud of her model. But in the end, she ended up with a decision tree that looks like this. And this is a very simple model again, but this is not interpretable anymore again, because the goal of this task was to produce some kind of guidelines for people who are putting up these projects so that they have a larger chance of being funded. But if you give them this decision tree, it's a mess and it's not interpretable at all. And that's just because the input variables are not completely independent. They are dependencies, and that leads to very long chains of decision rules that basically are very opaque and are not transparent and don't mean much to an actual person. So that was a little warning about using decision trees. And if you look at the Wikipedia article on decision trees again, the first advantage they are listing is that they are simple to understand and interpret. Well, only on certain data sets. On real world data sets, you end up with problems very, very quickly. So, sorry, that's just me screaming, not into the microphone, but in my slides about interpretability of decision trees. Now let's look at deep learning. The fanciest thing right now happening in machine learning. Everyone wants to do that. It's a lot of fun, etc., etc. So let's look at some deep learning demo. And in this one, I'll be using F# because why not? Because what I will be doing, I'll be calling the machine learning API from Microsoft called Cognitive Services. The thing is, I'm not picking out Microsoft right now at all. I'm not picking out Azure. If you were doing this with any of the other machine learning APIs, you would end up with exactly the same results. So this is just my wrapper code around using the Azure Cognitive Services API. This will be my function that I will call that performs the API request. And what I'll be doing, I'll be giving it pictures. And I'll be asking the API for tags for a picture and a description. And this function will just print it out. So let's test it. This is a very simple question, simple image. Okay, so what the API gave us as the answer or a description is that this is a close-up of a guitar. Okay, that looks fairly reasonable. And the tags it decided to add to this picture are music, guitar, musical instrument, string instrument, building material, not quite there, lumber, and bass. And next to each of these tags, you can see there is confidence that the API is giving to that tag. So at least the building material, the confidence is fairly low, but music, the confidence is very high. So that looks very, very good, right? So let's try something else. Let's try a monkey. And again, I'm trying to be as transparent as possible. This is literally the picture that I'm showing you. It's all marked down. So it's literally the same picture that I'm showing you is the picture that I'm passing into the API. And you can try it yourself later on if you are interested. So this is a monkey. And the description I got from the API is that it's a monkey sitting on a table. And the tags that got assigned to it is that it's a primate, it's an animal, it's a mammal, it's a monkey, it's sitting, it's a macaque. All right, that looks good, right? It's not really sitting on a table, it's sitting on some kind of railing, but it's fairly close. Let's try another monkey. Okay, and it's a monkey sitting on a branch. Even better, it is a monkey sitting on a branch. And the tags are tree, outdoor, primate, mammal, etc. Looks perfect, right? Let's put this into production. Oh wait, it is already in production because this is the cognitive services that are deployed. So let's try to break it. So one typical thing you would do when you are dealing with some kind of system like this is you give it something that's definitely not in the training set, that it has never ever seen before. So let's try this. This is a fairly disturbing image. So let's see what the API tells us about this. I call it a SMEAL, a smiling seal. So the results are, it thinks it's a close-up of a fish. And the tags are grass, outdoor, animal, eyes, fish, face, and clothes. Okay, so one thing, it doesn't see the teeth, which I think are the most disturbing aspect of this image. It doesn't tell us, okay, this is a really weird image and it's probably not a real animal. But I think it's doing a fairly reasonable job otherwise. It identified that it's something fish-like, which it is probably, and it's outdoor on a grass. So although it has never seen anything like this before, although it's a very disturbing image and the machine learning system is not surprised at all, I think it's doing a fairly reasonable job given the circumstances. So I don't think this is really breaking the system. But let's try something simpler. Well, let's try to give the monkey the guitar. Let's see what it does now. Well, it's telling me it's a monkey holding a guitar. I'm surprised. And there is a tree, there's a guitar, there's a sky, it's outdoor. Very good, I'm impressed. Well, what if we give the other monkey a guitar? And suddenly it's a dog looking at the camera. So why is it a dog? Well, my assumption is that because this picture is more indoors than the other one, it tries to match this to things it has seen before that are happening indoors. And indoors, a furry creature is more likely to be a dog. I'm surprised it's not a cat, but all right. But it ended up with a dog looking at the camera. Let's try another thing. Let's try to have the guitar just hovering in the air. And suddenly, this picture is a monkey holding a dog. What is even happening there? I have no idea, to be honest. One thing to notice is that the machine learning system, the deep learning system that underlines this, doesn't see the guitar at all. It just doesn't notice the guitar being in the picture. Although as a human, that's the first thing that strikes me, because there is literally a guitar hovering in midair. But it messed up the recognition because it decides that the monkey is suddenly holding a dog. So this did break the system in a way. So let's explore what's happening. Well, this is an example from the AI weirdness blog by Janelle Shane, where she tries all these things quite a lot, exploring how different machine learning systems work and where do they go wrong. And this is an example of a landscape. So let's see what description we get for that. It's a nice landscape, proper for social isolation. You can see there is just one person there standing in the middle of the picture. And the description we get is that it's a herd of sheep grazing on a lush green hillside. Well, you can zoom into the picture as much as you want, and there's not a sheep in there. What the API sees is that this is the sort of landscape where you might expect sheep to occur. So that's the tag it gives it. Another example, this is from my office. This is a meeting room in the Alan Turing Institute. I'm just trying to be a little nostalgic because nobody has been there in a few weeks. So let's give it to the API. And the description we are getting is that it's a man standing in a room, and it's indoor, and there's whiteboard, and it's an office building, etc. Fairly good. But what if we put an elephant in the room? What can cognitive services tell us now? Well, it's a couple of people that are standing in a room, and there's a whiteboard, and a computer, etc. 0 elephants. Thing is that the elephant is not something you would normally expect in an office, which means that the AI system just doesn't see that at all, because it's not something that should occur in there. So it's basically just shutting its eyes and thinking, okay, there's no elephant. So we are getting to some quite surreal images right now. Let's try to have the elephant hovering in midair. And suddenly it's again a monkey sitting on a branch again, and 0 elephants. So you can see a pattern happening here, that if there is something in a picture that is not supposed to be in there, that doesn't fit in there under standard circumstances, the machine learning system just doesn't see it. It completely ignores it. And let's try some properly surreal images. Let's try René Magritte, the Son of Man painting. And this is a man wearing a suit and a hat, 0 apples. Although that's the main thing that a human recognizes when they look at a painting like that. So, as I said, you can probably see a pattern that if there's something that it shouldn't be there under normal circumstances, the neural network just doesn't see it. The deep learning just closes its eyes, says, okay, there's no elephant in the room, there's no apple, there's nothing. So maybe the way to confuse these systems is to just wear apples in front of your face. Thing is, you probably see quite a lot of these articles on how to hide from the AI surveillance, blah, 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 with a colorful printout that basically prohibits the system to see you as a person. The thing is, all these systems are fairly complicated, and normally you do need access to the underlying deep learning network that's used for the image recognition, which you normally don't have because it's the state owning that. And these things are fairly complicated. You have to spend quite a lot of time constructing these things. But the thing is, the deep learning it looks more sophisticated than it actually is, and it doesn't really understand the image at all. It understands the patterns in the image. This is just an example from Reddit, where apparently when you have an Android phone, you take a couple of pictures in the same environment, then Google tries to offer you to combine them into a panorama. So this user decided, okay, yes, I want a panorama out of my pictures, and it turned him into a mountain. Because that's the right shape or whatever. And the underlying system doesn't have a concept of a mountain itself. It doesn't have a concept of a person. So it just meshes things together based on patterns. And the thing is, it very much depends on what we train them on. The problem with deep learning is that all these networks that are deployed out there, they are very much biased to their training data sets. This is an example from last year, where people in Facebook research published a paper, Does Object Recognition Work for Everyone? And what they did is that they tried typical images from low-income countries, classified them using all of these machine learning APIs. They used Azure, they used Google, they used Amazon, they used IBM Watson. They got exactly the same results, because this is not something depending on any particular vendor. This is a feature of the technology and feature of the data sets that we are training these systems on. So this is an example of a soap that I highlighted here, where if you try to classify the soap on the left from Nepal, it gets classified as food because all of these machine learning APIs, versus if you try the liquid soap on the right, then it gets correctly classified as something that's on a sink indoors. And that's, of course, a problem. Another example from last year, the self-driving Uber car that killed a pedestrian wasn't designed to see jaywalkers. It simply couldn't classify a person crossing the street outside of a pedestrian crossing as a person. It had problems classifying what it saw because it just wasn't expecting a person outside of a pedestrian crossing. The problem with these things is that they are very, very, very much dependent on the data. And I think you can see a pattern here, because the problem with data arose in the linear regression example. It came up with the decision tree example, and it's coming up now in deep learning as well. And the problem with machine vision and deep learning right now is that people are trying to deploy these systems into medicine. Well, I have a couple of examples from papers here. This is an example where they tried how well does a system generalize from one hospital to another, where they were trying to classify pneumonia automatically from X-ray images. And they trained a system that shows where is the deep learning system looking when it's trying to classify pneumonia. And in this image, you can see that it was looking at the shoulder of a person, which is way outside of the lung area. You shouldn't be looking at a shoulder of a person if you are trying to find out if the person has pneumonia or not. Why was it looking at the shoulder? The reason was that they had, in the original hospital where they trained the neural network, is that they had a system, sort of a mobile X-ray machine that they wheeled to the patients that were too sick to go to the proper X-ray machine. And when you put a patient into a machine like that, you give them a metal tag onto their shoulder to calibrate the machine. And the machine learning system looked at it and realized, okay, the patients who are too sick to go to a proper X-ray machine, the patients who have the metal tag, they are too sick, which means they probably do have pneumonia. So it used that as their sort of input, main input to decide if a patient has indeed pneumonia or not. This is another example. This is from last year, and it's an example of a system that's actually right now certified in the European Union to classify melanoma automatically. So what they did is they trained it on images of various skin lesions and skin marks. And what people in this paper did is they looked at that and they tried to break it by artificially adding violet surgical marks, the sort of marks that surgeons do on skin before removing a skin lesion. And of course, if they added a skin mark next to a skin lesion, the machine learning system automatically classified that as malignant because it zoomed onto that feature. It didn't look at the actual skin lesion. It looked at the violet marks that the surgeons would do around the lesion. So it was using a factor that's completely irrelevant if you are trying to decide if a lesion is malignant or not. And this system is actually certified to be used by medical professionals right now. To me, this is very scary. But really always boils down to the data, because deep learning systems, it's not magic. What they are trying to do is they basically just look at the data and try as best as they can to learn patterns from the data itself. And they are not distinguishing how sort of meaningful that is. They are literally just learning a mapping from input to an output as best as they can. So machine learning, it's actually no magic. It's basically doing exactly the same thing as software engineering in a way, where it literally just tries to learn a mapping from the input data. It's trying to learn what you tell it to learn, basically. And as much data as you give it, it tries to learn as much information as it can from the data set. So if there are always violet surgical marks around a skin lesion, it learns that it's a pattern for malignant lesions. So it uses that to classify malignant or benign skin lesions. Another example of that is, this is a fun example coming from MIT Media Lab, where they decided to construct the first psychopath AI system. called Norman. And what they did is they basically gave it ink blots to describe, but they trained it on texts from Reddit, from the darkest corners of Reddit. And excuse me. So this is a inkblot that it sort of just looked at, and a standard benign AI says that it's a black and white photo of a small bird. But Norman, the psychopath AI, says that it's a man getting pulled into a dough machine. And another example, standard AI would say that this is a person holding an umbrella in the air. Well, Norman says it's a man is shot dead in front of his screaming wife. So the thing here is that any AI system, it really just learns from the data you give it. And if you give it data from the darkest corners of Reddit, it learns to describe images appropriately based on that. And it only depends on the training data. It always comes down to data. Because the machine learning systems themselves, they are just learning what we give them. And if our data are biased, then their predictions will be biased. They are just mathematical models, and what we give them is what they learn. And before using any kind of machine learning system or any kind of black box, you should be asking about the training data that was used to train it. So where do the training data come from? How did the authors of the model pre-process the data? Did they look at things like outliers? Are there biases in the data? And if the answer is no, then probably you are just not looking hard enough, because every data set is biased in some way. Are real world data different from the training data? Is the model the right one for the data? And is your model doing what you think it's doing? And in this talk, I went through 3 different models. I didn't look at the mathematics. I looked at how they behave if they are getting data that they are not expecting. And you could see that even such a simple model as linear regression can get completely messed up if it gets a data set that violates its assumptions. And in case of the decision tree, the data were not the right format for a decision tree, and then the results were not what you would expect, or they were not interpretable, not as interpretable as you would expect. And in the deep learning example, it was mostly about the real world data being different from the training data and the data sets being biased. So the problem with any kind of AI is that it really just zooms on the data that you give it. And any AI system is only as good as the data. So I also like to use the metaphor of a data science iceberg, where the fancy models are just the tip of the iceberg. The deep learning systems, the fitting of the models, of choosing which model to use. At the bottom of the iceberg, the real mass of data science is actually dealing with the data. And quite often you do need some domain knowledge. You need to understand the domain. You need to know what's happening to identify where your system is going wrong. And if the machine learning algorithm you are planning to use is actually the right one for the task you are trying to solve. So I'm not afraid of the AI taking over. When it can solve video conferencing, then I might be afraid, but I'm not afraid right now. I'm afraid of people using AI incorrectly, of using our current machine learning models to do decisions and to affect people's lives without properly validating the models and without using the right model for the right job. And I'm afraid of people using these models with biased data, which means they just won't work for a lot of people and for a lot of cases. So that was my talk. Here you can see a link to my GitHub with all the Jupyter notebooks that I used, and you can play with it yourself. You can try these things with your favorite machine learning libraries. The thing is, especially with the deep learning one, you will get exactly the same results, whatever platform you use. As I said, I used Azure, but you will get exactly the same results with Amazon. You get the same results with Google. So please do play with it. And I hope I made you at least a little paranoid before you do that and before you put anything like that into production. Thank you. So isn't this a more general problem with machine learning dealing with data set? Human beings can generalize, have abstract thoughts, and use common sense. Well, that's exactly the thing, because machine learning doesn't have any common sense or any concept of a common sense. But people sort of implicitly assume it does, or they give it sort of more credit than it deserves. Because machine learning systems are just trying to learn patterns. They're just trying to learn mappings from your data sets. And it's really the main message of this talk, because I see a lot of people just using machine learning without thinking and without really analyzing what's happening there, putting it into production. But machine learning can't generalize outside of its training data set in general, or it's very hard to do that, and doesn't have any common sense. Now, the next question is, humans can see a face, whether it's on a painting, cartoon, or upside down. We don't scan the pixels and look for patterns. Well, that's actually a fairly known factor in humans, that we see faces even in places where there are none, because our brains are sort of wired to see face-like patterns whenever possible. Deep learning actually works fairly similar, or at least the sort of standard deep learning we are using for image recognition, the convolutional neural networks. They are actually fairly similar to how visual cortex works in humans, where it's sort of very layered design, where first you look at sort of things like lines and very small patterns, you construct them into larger shapes, etc. We don't really look at pixels. We do look for patterns, though. But the big difference is how we interpret that. And with machine learning systems, they are not very good at that. I hope I answered the question. And the third question I have here is, can you, via mathematics, implement abstract thought and common sense thinking? So you don't need to provide lots of images of faces. It learns and generalizes. I think this is right now the sort of the main goal in machine learning. That's the golden grail of machine learning right now. If we could do that, then we would probably have quite a lot of sort of human-like thinking. We can do this in very small settings where the task is very well defined, where the task is very, very small, and we can make a lot of assumptions. Then it's fairly easy. But in anything more general than that, it's very, very difficult. And a lot of people are trying to work on that. And it looks like standard, let's say, deep learning can't really do the whole thing. It can go only so far. So if there are no more questions, then I would like to thank you for your attention, and we can take the any more questions or discussion onto Slack.